Section 11.3, area and the definite integral. In section 11.3, we're going to briefly touch on the theory. I know how much we all love theory. Before we move on to section 11.4 and see how the theory is applied to many examples. If you look at this example, what is a certain state's total petroleum consumption during the time shown below? This would be easy to determine because it's a shape we're all familiar with, that being a rectangle. So all you'd have to do to figure out the total petroleum consumption is determine the area of this rectangle, which would be 4 times 1.2, or a total of 4.8 million barrels. But what if the graph changed to something that's more realistic? Well, I don't know about you, but I have no idea how to determine the area under this curve above the t-axis. Okay, so we could approximate that area by doing this. We could come up with maybe 4 different rectangles that might look something like this. This is just one possible way of approximating the area. Come up with rectangles like I'm doing here. And then, because we have, 4 rectangles, we could determine the area of each of these rectangles because we know that the width is 1 unit for each one. And then we could approximate the height and ultimately come up with a good approximation. Maybe not a good approximation, but an approximation of the total number of barrels of oil based on this graph. But what we want to do is come up with a way that's going to make it very, very precise. And that's based on this Riemann sum. So long story short, what Riemann sum is going to allow us to do is come up with infinitely many rectangles. And if you had an infinite number of rectangles, you are really looking at the very precise area under a given curve. This is going to be that notation. This is just telling us that the limit of all of the areas of the n number of rectangles as n approaches infinity is going to be equal to that definite integral. That's what we're going to be calling it now. So this notation is what we want to be focusing in on. All this other theory, you're not going to be tested on that. All right, so don't worry about that. And let's go ahead and move on to section 11.4. All right, section 11.4. This is the big one, folks. This is one of the most powerful theorems in all of mathematics, the fundamental theorem of calculus. So we're going to be doing the same thing here as we did in sections 11.1 and in 11.2, except now we're going to be actually able to evaluate these, and they're going to be called definite integrals. All right, definite integrals, because we're going to have a definitive result. So how do you do it? You take the the antiderivative of this, which will give you some new expression, and then you're actually going to plug in what's called the upper limit of integration into every x you see in your result, and you're going to subtract that from the value you get with respect to the lower limit of integration being plugged into every result you got for the antiderivative. Okay, let's get to it. We're going to do what is stated here and highlighted in yellow. Let's apply this theorem to some examples. In this first example, we are actually going to be determining the area of a given region under the graph of this curve. Okay, but we need to understand that when we evaluate definite integrals, we're not always going to be getting the actual area that's bounded over some closed interval. Okay, so I'm going to be explaining that by way of looking at this example and then also looking at example number 2. So we want to make sure we're paying attention to these differences. All right, so in number 1, here's what we're going to do. The area is actually, in this particular example, going to be equal to this. So the area underneath this curve on this closed interval from 0 to 4 is going to be equal to the integral of the function with a lower limit of 0 and an upper limit of 4. All right? Okay, so what does this give us? Well, again, we're going to handle this just like we did in section 11.1. So we get 4x squared over 2 minus x cubed over 3. And then we're going to put parentheses around this, and we're going to actually be evaluating this definite integral from 0 to 4. There's your lower limit of integration and your upper limit of integration. All right, so what does this look like? Well, let's go ahead and reduce this. 4 over 2 is 2. Here's what it looks like. 4 over 2, 2. Now, everywhere I see an x, I'm going to be replacing it with my upper limit of integration. So it looks like this. So what we've actually done here in this part is determine the value of f of b. Very good, everybody. And now in our second part, what we're going to do is the same thing, except now wherever we have an x, now whenever we have an x, we're going to replace it with the lower limit of integration. So that looks like this. So this really is representative of f of a. That's the fundamental theorem of calculus. Capital F of b minus capital F of a. What is capital F? Well, it's the antiderivative of the given function, or the integral of this function, okay? All right, so now all we have to do is evaluate. So what do we get here? 32 here, minus 64 thirds here. And this is just minus 0, so that's nice. And then let's say 32 minus 64 thirds. 32 thirds, I believe. So 32 thirds. In this case, it is units squared. Now, like I mentioned at the beginning of this example, let's go into a little more depth so that we understand that it is actually an area in this specific example. So if you were to make a sketch of this graph, it would look something like this. I'll do the best I can. It's going to be a parabola, all right, like that. And it's going to go through x equaling 0 and then x equaling 4. So this is actually my function f of x right here. There's my y-axis, there's my x-axis, okay? Well, the reason why it is actually the area in this case is because if you look at the graph of this curve over the closed interval from 0 to 4, the entire curve on that interval is above the x-axis. In other words, every y value on this open interval from 0 to 4 is positive. So what we actually just determined is the area of the bounded region below the graph of f and above the x-axis. That's what this is equal to. Let's go on to example number 2.